Hi, welcome to this short presentation about Zynq Extensible Processing Platform being applied for a high-definition video processing application. I'm Navanee Sundaramoorthy, part of the processing platforms team at Xilinx. Welcome. What I'm going to talk about is Zynq Extensible Processing Platform. What it is a combination of a dual-core Cortex-A9 processing system with standard peripherals like Ethernet, USB, DDR3 memory controllers, all in a hardened subsystem, almost like a standard ASSP, connected along with it on the same chip with some programmable logic, which is the extensible part, which allows you to extend your system and makes it very flexible. So this combination of a hardened processing system with a flexible programmable logic allows you to build fairly interesting, intelligent video processing applications. Let me talk about that for a second. So when you take intelligent video, what do we mean? These days when you take surveillance applications, machine vision, automotive, or various applications like these, what the industry is going towards is high definition video. So you need to process high definition video at HD or higher data rates and 30, 60, or 120 frames per second and be able to handle that much data, do some processing, not just to buffer something or encode it and send it somewhere, but actually do something intelligent right at the device level. So that's what the Zynq Extensible Processing Platform is really designed well to do. And I'm going to show you one simple application, which is, you could say, part of the application which shows HD processing. What we have here is the Zynq Z7020 board, which has a Zynq 7020 device on it. It's got some Ethernet network interface, an SD interface. This is where I'm going to boot my Linux operating system from. And the Zynq runs using the DDR3 memory with networking and UART and various peripherals. But apart from the processing system, I also have the FPGA programmable logic, which is hooked up to this FPGA mezzanine connector. And I have this AVNet DVI FMC card, which has HDMI interface in. So I have video input coming in to this card and the video output going into the monitor, and that's all connected on this Zynq development board for doing video processing applications. So from the laptop, I'm driving through HDMI output onto the board. The board is going to do the processing and show it on the monitor. So when I run this, what first stage I'm going to do is, in order to do the processing, first time anyone is working on a new algorithm, what you'll do is you'll actually run the algorithm in software. So first I'm going to run this application in this default mode. What it'll do is it'll just bring live video input in, and in my hardware design I have this DMA that takes it into the DDR3 memory that's hooked up the processing system, and it's getting buffered there. And then in the next stage I have another hardware block which can do a video processing, in this case an edge or feature detection using Sobel filter, and there is a display controller. That's the piece that I have. At first I'm just going to get live video in and use the display controller to display it. And now you can see the live video, and the video is clean. I have a small video playing, which is this musical instrument, whatever, and you can see the video input. It's looking good. What you now see is the system is able to keep up with 1080p 60 at 60 frames per second. So the system is capable of handling that much data coming in and going out of the system. Now I'm going to do this software-based filter, use the CPU to run this feature detection using Sobel filter. Let me turn on this application. In this mode of operation, the CPU is going to take all of the video coming in and do an edge detection. It's a 3x3 Sobel filter. It's going to do operation on it, and the results are going to be buffered in memory, which is going to be displayed by this display controller that we have from our partner Cylon, who has a display controller. Now this application is running fully on the CPU to do this operation. When I run this application, let's look at the CPU utilization. So in this Linux top application, when I look at the CPU it says 50%, which means it's half of this two scores, or 100% of one full CPU is utilized just to do this Sobel filter. And if you look at the video is slow. It's about 5 frames per second. You're missing frames. You're not seeing the balls move in the video properly. That's because the system is not able to keep up. The CPU is not able to keep up with that algorithm. Now that from an application standpoint the algorithm is working correctly, you can see the edges are all correctly detected. So what we did in order to port this application to hardware was we used our auto ESL tool flow. So traditionally, if you have to do FPGA design, you have to do RTL, VHDL, Verilog development, then it's usually difficult for video application developers. But in this case, to make the flow easier, what we did is we took exact C code that we ran in the CPU, used the Xilinx auto ESL tool, which takes the C code and is able to create the hardware logic on the FPGA. So we converted that same algorithm. We did not modify the algorithm. We take the same algorithm without any modification, created the hardware using the auto ESL tool, and we plugged it into the programmable logic. Using a DMA, we hooked it up so that you can get video through the hardware. So let's turn on the second mode of operation. In this case, it's going to do all the operation in hardware. When I turn this on, what happens is now the video is able to keep up with this for 60 frames per second. You can see it's clean. It almost looks like the original video. So if I switch back to the original video, the video looks similar, the original video and the edge detected video. That means system is able to keep up. And now let's look at the CPU utilization. The CPU utilization is almost 0, which means both the CPUs are readily available to do the real end application. Now we've offloaded what was taking 100% of the CPU fully to this programmable logic using a C to hardware tool flow, and the CPU utilization is low. Now the rest of the CPUs can be used for the full application, which will be something intelligent running under Linux, using the network interface, or doing some higher level operation after feature detection. So that's what the Zynq processing system allows you to do. It allows you to handle high definition video, process it, do algorithms in the CPU, and when the algorithm's right, and if you want to optimize the critical portion, you can offload it to hardware and meet high performance real application needs. So that's the value of the Zynq processing system for high definition video processing. Thanks for watching.